This is ECE 343 Signals and Systems. This will be the fourth part of Chapter 2. Last time we introduced the idea of convolution. This lecture we will spend some time going through several examples of carrying out the convolution integral, and then we'll look at some properties of convolution that give us additional insight and help simplify certain convolution operations. On our first example that we're going to do, let's go ahead and take a signal x of t that is a unit step function, and then also take a signal h of t, which is a unit step minus a shifted unit step, making a unit duration, unit amplitude pulse. So we have x of t equals a unit step, and we have h of t just being that unit duration, unit amplitude pulse. I'd like to go ahead and figure out the convolution of these two signals, and we'll call that result just y of t. First order of business then is to carry out that step one, which is to plot both x of tau and h of t minus tau. X of tau is no problem. We're just replacing the variable t with the variable tau, and we get a unit step looking function, which I've drawn here in blue. If I want to go ahead and get that h of t minus tau, we can think of that as a two-step process. We first start out with h of tau, that's our unit duration, unit amplitude pulse, and then we flip that about the vertical axis that's shown in the next graph down, and then we shift it by some value t. So we just get a shift in t. The amount of shift depends on the particular value t that we're interested in. Notice that whatever was at value 0 in h of minus tau becomes a value t in the shifted one, h of t minus tau. That just makes a nice, easy way of tracking points. In this plot of h of t minus tau, we should always label the edges with the corresponding values. So this is a function of tau, and we know that that leading edge is identified by tau equaling t, and the last edge, the lagging edge, is identified by tau equaling t minus 1 unit to the left of that leading edge. So if I was going to redo step one or summarize step one, what you might do in a typical piece of paper, I'd go ahead and plot out x of tau, and then I'd go ahead and plot out h of t minus tau, the flipped and shifted version of h. Step two involves looking at region that starts out at minus infinity and goes up to some amount or some time that that convolution integral has a particular fixed form. So we're going to try to go ahead and demonstrate this with a little bit of a motion. We know that our output, y of t, is a function of time. We're looking at different values of t. We're going to be looking at a group of values of t for which that integral, the integral of x of tau times h of t minus tau, has a particular form. I've gone ahead and covered or collected together that signal that is h of t minus tau, and I can move that around anywhere that I want to. In this particular case, what I would like to do is I'd like to think of moving this out with a big negative time. So if I have a big negative time, that lead edge, which is located at time t, or at tau equaling t, right? That's going to be way off to the left of the edge of x. And if you look at those two guys and how they interact, h of t minus tau times x of tau at that kind of orientation, any of these values that I'm showing here, any of these values of t as I move this guy around so that the h of t minus tau is to the left of x of tau, the product of these two guys is going to have a very particular form. It's going to be 0 everywhere. So if I had a t here, it's going to be 0 as a product. If I had a t way back over here, it's 0. Any of these values of t, as t moves from minus infinity across all these different values, I'm just getting a product of x of tau times h of t minus tau as being 0. That's true until that lead edge of h of t minus tau, which is identified by t, hits that value of tau equaling 0. Once I hit tau equaling 0, then I start getting some overlap, and the form of the integral, what I integrate, is no longer going to be an integral of 0. It's going to be something different. That will be a different region. So for right now, I'm working on the first region, and I'm just going to leave this shifting around h of t minus tau at a representative location. I'm going to put it something like that, and I've got a value t less than 0. So my first step, or my first order of business here, is to visualize how h of t minus tau is interacting with x of tau so that the integral has a particular form, and for what values of t does it do it. And we just saw that this goes up through t equaling 0. So from minus infinity to 0, what do I know? I know that the integral from minus infinity to infinity of x of tau times h of t minus tau, the product of those two, as shown right now, is equal to 0. So I'm integrating up a 0, right, over all time, and that's just going to give me out a 0. So this first region, really easy, right? I get a value of 0 because the product x of t, or x of tau, times h of t minus tau, that product is 0, and an integral of 0 is 0. The next region, so this is step 3, I pick up and repeat step 2 for all the different regions that I can find. In this particular case, region 2 is going to pick up where the last region ended. So if I take a look at where the last region ended, it ended at t equaling 0. So I'm just going to copy that guy down here. So this next region has to pick up where the other one left off. And I need to figure out how long this next region lasts. Let's go ahead and do the same sort of game where I'm going to go ahead and grab that h of t minus tau, and I'm going to allow myself to move this guy across the other waveform. We had already handled the step over here where that pulse is to the left of the unit step x of tau, right? Now we were looking at when that pulse is entering the unit step. In that particular case, the integral of x of tau, h of t minus tau, will have a particular form. It's going to be non-zero on the interval 0 to t. 0 because the leftmost part of x of tau dictates where the leftmost part of the non-zero product is, and then the upper limit of t is dictated by that rightmost edge of the moving pulse, right? That's the last part where the product of those guys is equal to 0. Now, if I kept moving my t in here, I could eventually get over here where that pulse is fully contained in the unit step. That's going to be a different region because the form of the integral is going to change just a little bit. We'll see that next time. So we don't want to talk about the case when the pulse is fully within x of tau. We don't want to talk about the case where the pulse is fully out of x of tau. We want to talk about that case where we're just moving that pulse into it. So I'm again going to just pick a point where I see something that's representative. So I show a case here where I've got that pulse, which is dictated by h of t minus tau, and it's entering this portion of x of tau, and I'm thinking about the product of these guys. Now the product of these two is 0 for all tau less than 0. So the integral from minus infinity to 0 is just going to be an integral of 0, and you're just going to get 0 out of that. From 0 to t, the product of these two functions is 1 times 1. And so that's a non-zero value, and I'm going to need to deal with that integral. As I continue that integral to get out to infinity, going from t to infinity, I'm going to get 0 times 1. That's just a product of 0. And so again, that's just going to be an integral of 0, and that's going to disappear and be 0. I'm going to go ahead and be quite complete in the way I write out the integral. In this particular case, normally you wouldn't include all these 0 terms. I just want to demonstrate that they're all there. So we had an integral, right, that went from minus infinity to infinity. We still have to be dealing with that, right? I'm just going to break it up into the 3 pieces because the product of x of tau times h of t minus tau is a piecewise function. And the first piece goes from minus infinity to 0, and over that part, it's 0. And then I'm going to add to it, right, the integral from 0 to t, and the product, x of tau times h of t minus tau, over that interval, 0 to t, right? The x of tau function is 1, and the h of t minus tau function is 1. So I'm going to get 1 times 1 d tau. And then I'm going to have that integral going from t to infinity. That gives me the full integral from minus infinity to infinity. And going forward of t, right, the h function is 0, and the x is something non-zero, but 0 times something non-zero is still 0. So I'm going to get a 0 in there as well. So when I take a look at this particular case, right, this first part goes to 0, the last part goes to 0, and there's only one other part left in there. That's the integral 0 to t of 1 times 1 d tau. So that's an integral of 1 d tau that integrates to tau, right? Evaluated on the limits 0 to t. If I go ahead and do that, I get out t. So y of t is equal to t. It's just like a linearly increasing function over the interval 0 less than or equal to t less than what? Well, how long does this guy last? This thing lasts until the very last edge, right, of my function. That last edge of my function is identified by t minus 1. When that last edge hits the beginning of x of tau, right, that's going to be when that pulse transitions from entering x of tau to being fully within x of tau. So that occurs when, when t minus 1 equals 0, the region ends. The region ends. So that's going to be t equaling 1. I'll go ahead and plug that guy in there. And so I'm going to have this next region, right, this region 2, taking all values t less than or equal to 0 all the way up to 1. Okay, so I've taken a couple regions. The next region is going to be when that pulse is fully contained inside x of tau. So we're going to continue step 3, which is just repeating step 2 for every region there is. I'm going to again do the same sort of operation here. I'm going to go ahead and grab that h of t minus tau. And just a reminder here, we had region 1, right? That was for t at 0 and less. For 0 and less, right? H of t minus tau times x of tau is going to give us 0. We have an integral of 0. So for t less than 0, we get 0. When t hit 0, right, we transitioned to a new region. That was region 2. And that was when this pulse, this red guy, right, is entering x of tau, that unit step looking function. So that happens starting at t equaling 0. That's when the overlap first starts. And it continues until what? Until that edge, right, t minus 1 is perfectly lined up with the left edge of x of tau. That's at t minus 1 equaling 0 or t equaling 1, right? After that, we're going to be in region 3. And in region 3, right, we have that pulse fully contained inside that unit step. It's fully contained when it first gets in, when t minus 1 is going to be greater than or equal to 0. And it stays that way no matter how far to the right I move that pulse. Because in all cases, because that unit step stays 1 forever, we're going to have that pulse, that red pulse, fully contained in that unit step x of tau function. So I'm going to again just pick a representative orientation for this region. So I've gone ahead and done that. I know that the region here, region 3, picks up where the last region was. So the last region ended at 1. And that just means that my next region, this region 3, starts at 1, right? And it's going to go out until the region ends. And we found out that that guy goes out to infinity because that pulse, that red pulse, right, is fully contained in that unit step going from t equaling 1 all the way out to infinity. Now, in this region from 1 to infinity, right, what does my integral look like? Well, I'm going to have 0 as the product, x of tau times h of t minus tau. That product is going to be 0, right, for all tau less than t minus 1 and greater than t. So it's actually the h function that is going to determine the limits of integration in this case. So my limits of integration are going to go t minus 1 to t. Why do I get that, or how do I get that? If we just take a look at it, right? If I look at when the functions are both non-zero, I can show some edges here in green, right? Between those two green lines is when x of tau and h of t minus tau are both non-zero. That's where we're going to get some part of this integral. What are the values of x of tau and h of t minus tau over that overlapping part? Well, they're each 1, so I'm going to get 1 times 1 d tau. And where do I integrate from? This is all the values of tau for which that is true. And we can see that based on our labeled graph, right, that goes from t minus 1 to t. So it's very common that what we will see is that the edges, how we have the edges labeled, what values of tau are those edges, right? Those come in and start helping us decide what our limits of integration are. All right, so if I go ahead and I carry out this particular integration, I have an integral of 1 d tau. I already know what that's going to be equal to. That's just tau. And I'm going to evaluate it the limits of integration. That's going to be t minus 1 to t. Take a look at what region 2 was. It was very similar, right? The only difference was that its lower limit was 0, where this guy has a lower limit of t minus 1. This is not unusual. This is a very kind of typical kind of behavior where you might find the difference from one region to the next is only just a change in a limit of integration, for example. Or maybe you're just going to change one little part of an argument of an integral. But those small changes, as small as they might be, are important, and they're systematic, right? They're consistent. This third region has that non-zero overlap between x of tau and h of t minus tau on the interval t minus 1 to t, and it's 1 times 1. So I'm going to go ahead and carry out that operation, evaluating at the limits of integration. I'm going to get t minus, and then I'm going to get a t minus 1. So t minus t is 0, and a minus of a minus 1 is equal to 1. So I end up getting a value 1 there. I've covered the entire set of possible values for t going from minus infinity to infinity. And so I'd like to pull all of my results together and put it into a single expression. So my final result here, region 1, if you will. So if you remember our region 1, that went minus infinity to 0, and we knew we had out a 0, right? And then we picked up that last region to start into region 2. Region 2 started then at 0, and it was 1 unit in width. That was when the pulse from h was entering the unit step of x. And over that part, we know that we got that convolution integral, the integral evaluating to a value t. And then on that last region, region 3, that picked up where the last region ended, so that 1 carries forward, and this one happened to be the last region, so it goes all the way out to infinity, and in that particular case, the convolution integral evaluated to a value of 1. If I was going to go ahead and plot this then, let's take a look at what this guy looks like. Right, so I'm going to be looking at the convolution integral y of t as a function of t, and what I can say in this is that for all times less than 0, right, I got 0. That's all part of region 1, right? And then region 2 was where it starts going linearly, so I could put in a value t in there. This was my region 2, so from the interval 0 to 1, this output grew linearly. And then if I was going to look at the last part, right, region 3 is t greater than or equal to 1. It just held flat at a value of 1, something along those lines. When I look at these all together, my final waveform here, you'll notice is smooth, right? It transitioned from 0, and then it went straight up, right, to a value of 1. And I never did have to take my pen off the paper on this. This is typical. This is something that is going to happen as long as you are convolving functions that don't involve delta functions. So if you're just convolving regular old functions, when you convolve those guys, because of the nature of accumulation in that integral between just regular ordinary functions, you'll see that it's always consistent. Why do I bring this up? It's really common for us all to make some sort of mistake in our integrals. For example, I might have in region 3 computed out the integral not to be 1, but I might have computed it out to be like a half. Let's go ahead and draw that in there. I know this is incorrect. I had in there region 3 equaling to a half. And what I would notice in here, if I was going to look, I'd notice that sharp edge going between region 2 and region 3. The fact that I transition and I have this sharp edge, this jump discontinuity in the waveforms, right, from region 2 to region 3 is a big warning sign. It's this big indicator that I've got a problem in my convolution integral. This, of course, again, is only true if I'm convolving functions that don't involve delta functions. So if I had gotten that and I saw that jump discontinuity in this result, I would know to go back. And in this particular case, I probably wouldn't worry about region 1 because I see that matching up with region 2 just fine. I would be concerned about region 2 or region 3. And just based on what I would be seeing there, I'd probably be guessing on region 3 because region 2 matched up with region 1, but region 2 wasn't matching with region 3. Process of elimination, maybe I guess that it was region 3 that had a problem. It gives me a little bit of information on maybe where to go to try to go back, find out what my math error is. Oh, it wasn't a half, it was equal to 1. And then you go ahead and get it in there and you get this nice smooth waveform. So that's another example of convolution. This one took a finite duration h, right? Times or convolved with an infinite duration x. And what we found out in this particular case is that there were 3 total regions. The first convolution example we did in our last lecture only had 2 regions. Okay, well, let's move up and work on a slightly more complicated convolution problem. In this particular case, I'm going to take a signal x of t, which is ramping up, right? So it's going to start at a time 0, end at a time 1, and at time 1, it's going to have ramped linearly to a value of 2, and that's drawn in there in blue. I would like to convolve that with a unit duration function h, which has a peak value of 2. So it's just a 1 duration, 2 amplitude pulse, okay? And I want to go ahead and carry out the convolution between these two. Step 1 again is what? I need to plot these functions, right, as functions of that variable tau. X of tau, just leaving the function alone. H of t minus tau is a flipping and shifting, right, of my h function. H of t in this example is very similar to the h of t in our last example, except for its height is 2 rather than 1. So we already kind of know what this guy looks like, and I'm going to go ahead and just draw that in here. We don't have to spend too much time in there. When I take h of t going 0 to 1 and I flip it, that means it goes from -1 to 0. And when I shift it, I just add t to all those edges. So -1 plus t is the t minus 1, right? And the 0 plus t is just going to give me the t. So those are my 2 edges. And it's of height 2 now instead of height 1. The other guy, x of tau, because I'm just looking at x of tau instead of x of t, it looks exactly as x of t. I just replaced t with tau. So it's going to look exactly the same. It looks like that ramp function that ramps up starting at 0 and ends at a time tau equaling 1 with a value of 2. It is really important at some point, and this is a good point to do it, to give a parameterization for all the pieces of our waveforms. In some cases, these parameterizations are pretty boring. So for example, x of tau for values tau less than 0 is all 0, and that's probably not something you have to write down. We can see that that's just a constant 0. Same sort of thing out there for tau greater than 1. We see it 0. But between 0 and 1, we see that this thing linearly changes. We need the equation in terms of tau that describes that variable x of tau. In this particular case, we have a straight line that intercepts 0, so the intercept is 0. We only have to worry about the slope. The slope here is, it rises 2 for every unit length of run, right? So we're going to have a slope 2. So we should have here a 2 tau parameterization. I can check that out, right? Put in tau equaling to 0, which is really me looking at what happens on that leftmost edge. When I put tau equaling 0, I get 2 times 0, that's 0. And sure enough, that's exactly where I've drawn that green dot. At tau equaling 0, that parameterization, 2 tau, 2 times 0 does evaluate to 0, exactly as the curve would expect. If I go to the other side, when I pick tau equaling 1, I can plug that into my parameterization. I get 2 times 1. That's going to be a value of 2. So at tau equaling 1, I'm going to get 2 times 1, or 2. And that also intersects what I see that waveform to be. I would encourage everyone, when you're drawing these waveforms, whether it's just the regular waveform left by itself or the flip and shifted version for H, we do need to get these parameterizations, and it's worth checking that the parameterization gives you the values that you expect, just to make sure you did it right. If I have 2 points and an equation for a straight line, I know what the rest of the points are, so I definitely know that that guy is going to fit in there. Okay, I think I have everything I need in order to move on to step 2. Step 1, recall, just says plot x of tau and then plot h of t minus tau, both as functions of tau. X of tau just looks like the normal function, right? H of t minus tau is a flip and shifted version of the original function, h. So step 2 says, let's go ahead and start at a big negative time, t equals minus infinity, and continue on for all those times that the product of x of tau and h of t minus tau have a particular form. This region is where that product is going to have a particular form, so that we can just evaluate that form once for all these different values of t. I'm going to do this just like I did before, so I'm going to go ahead and grab that function h of t minus tau. As we look at different values of t, right, all that does is it moves that function h of t minus tau relative to the other function x of tau. So looking at different values of t, I just slide one against the other, so I'm doing a sliding operation. If t is big and negative, right, that pulse is way off to the left, and we can see that the product of h and x is just 0, right? There would be just a product that gave us a total of 0. And in fact, it's 0 for all the places, all the positions that I'm showing here, until what? Until that lead edge of that pulse hits right where that x starts becoming non-zero. That occurs at t equaling 0. So our first region is all values t less than 0. I'll just pick one and go ahead and leave it as a representative case. For all values t less than 0, right, we get just like we did in the previous problem. We are going to have an integral of 0, which is going to give us out a 0. So this first one, pretty easy. There was no overlap between the two functions, right? And so we know an integral of 0 just gives us 0. The next region, step 3, says continue step 2 for all possible regions. The next region picks up where the last region ended. So if I go ahead and take a look at our last region, it ended at 0, and that means that on this region 2 for my next region, it's going to start at 0. So 0 less than or equal to t, and then we need to figure out how long this next region lasts. How long does the next section, where h is now interacting with x a little differently, how long does it have a particular form that we can do with a single computation? Again, I'm going to grab my function here. You'll get to the point at some point where you aren't going to have to maybe do these kind of graphics, but I think until you get that mental image going on in your head, taking something that allows you to move one relative to the other, whether you cut this out on pieces of paper or whether you grab a kind of an electronic device like I'm using right now, this iPad that lets you move one waveform next to the other. You need some way, probably graphically would be the most beneficial, to help you visualize how these two waveforms are interacting, and that will inform you how to write out your equation for the integrals. So I'm going to go ahead and grab this guy again. We had region 1, right, over here where that pulse had not had any interaction with the x of tau pulse. Now we're starting where what? Where that rectangular pulse is now entering the triangular pulse. When I'm entering in there, it's going to have a particular form. At some point, though, right, that pulse is going to not be entering, it's going to be exiting. That exiting is going to be another region, right? And then we're going to have another region where that pulse is completely exited. It's no longer having any overlap as well. So I'm getting an idea on this problem that there's not going to be 2 regions, not going to be 3 regions, but there's going to be 4. One region over here where this pulse hasn't hit my triangle function, one region here where the pulse is entering that triangle, one region where that pulse is exiting the triangle, and then there's one region where the pulse is past the triangle, right? Something like that. So right now we're on region 2 and we're entering that triangle, and I'm just going to leave my graph at a representative location, something like this, so that I can think about their interaction and hopefully draw out what the integral is. Y of t is an integral of the product of these two functions. If I look at this guy, what do I get? Well, anything from tau going from minus infinity to 0, that product is going to be 0, right? Because at least one of the two functions is 0 for tau going from minus infinity to 0. For tau going from 0 to t, I see that both functions are non-zero, and that means their product is going to give me something non-zero. So on the interval 0 to t, right, both functions are non-zero. One of the functions is 2. That was my h of t minus tau. The other function was, if you remember, we had done the parameterization there, right? That parameterization was 2 tau. We knew that the height of our sliding function was 2. So we already put in the 2 there. Now I need to go ahead and put in what the other function was, and it was 2 times tau, something along those lines. And then we'd be doing a d tau. For tau going from t forward, from t to infinity, right, we know that at least one of the two functions, x or h or both, are 0, so the product is 0, and it will contribute nothing to the integral. So again, we're left with a single integral. The integral's limits are dictated by those edges, right, and we just need to make sure that we're paying attention to what the parameterization is for each waveform, and we multiply those guys together. Now I'm ready to do the calculus. The calculus is the easy part, right? It's the visualization and setup that makes these problems a little challenging at the start, just because we haven't done a lot of them before. But once you've got it set up, it's nothing more than kind of like Calc 1 and Calc 2 type of stuff. So I'm going to have an integral 0 to t of 4 tau d tau. What is the integral of 4 tau d tau? Well, if I integrate tau, I'm going to get tau squared, right? It would be divided by 2, but then it was multiplied by 4, so that's going to be a 2. You could check this out by differentiating that, and I would have gotten 4 tau, which is exactly the argument of the integral. This thing's going to have limits of integration, right? That went 0 to t, so I need to put those guys in there. If I go ahead and do that, I'm going to get 2t squared, right, minus 0, so it's just going to be 2t squared. All right. So I have now gotten a curve, or a parameterization, an output, an expression for my output y over the interval 0 to what? Well, again, it's just like before. It's until that lag edge of h, which is identified by time or tau equaling t minus 1, until that guy hits, right, the starting edge of x of tau, which is at 0, we're going to have that pulse entering. So for as long as tau minus 1, right, until it equals 0, we know that this region has got that pulse entering. So if I solve that through, I'm going to get t equaling 1. So this region is again going to be 1 unit in width. By the way, we could have probably guessed that. Look how wide is the red pulse. The red pulse, right, that's the h of t minus tau, that's the one that's moving. That pulse is 1 unit in width. right? It's moving into another object. It's not too surprising that the region here where we're saying that that red pulse is entering something happens to match the width of the pulse, right? Because it's going to take as wide as the pulse is for that guy to enter the other waveform. So in this particular case, it went 0 to 1. Next region picks up where the last region ended. So we're going to have 1 less than or equal to t, and then it's going to go on for some time, right? And this is the case where the pulse is going to be exiting that triangle function. So I'm going to go ahead and grab the pulse and just take a look at it. So over here was region 1, pulse hadn't entered anything. Region 2 is where the pulse was entering the triangle function. Region 3 is where that pulse is exiting the triangle function. And eventually region 4 is going to be over here when the pulse is exited. When does it exit? Well, it exits right there at that location. When the red pulse left edge, which is identified by t minus 1, right, is equal to, right, x of tau at its rightmost edge, which is at tau equaling 1. So when t minus 1 equals 1 or t equaling 2, that's when this thing is going to quit exiting that blue triangle. So we know that the rightmost edge of this region 3 is going to be at t equaling 2. Again, it's 1 unit in width. If you look at here, I had my width 1 pulse, and it was exiting from this other object, and that width 1 pulse is going to take the full width of 1 to exit. So not a surprise that this region is 1 unit in width. So I'm going to go ahead and pick a representative value here and go ahead and do this. I would encourage you to draw something like this even as you're going through the regions so that you can visualize, right, how one waveform is interacting with the other. I've already got an idea of when this ends. It ends when t minus 1 is equal to 1, or that is t equaling 2. So this next region went from 1 less than or equal to t less than 2. And in that region, what do I get? The product, x of tau times h of t minus tau, is non-zero, only going from, well, the lower limit is going to be dictated by the h function, its leftmost edge, t minus 1. So my lower limit is t minus 1. And the upper limit of where these two functions are both non-zero is going to be dictated by the blue triangle, and that's at tau equaling 1. So the limits of integration here go tau minus 1 to 1. And it is, again, going to have a product in here that's going to be 2 times 2 tau d tau, just like before. So the h of t minus tau function is 2. The x of tau function is 2 tau over that part of it. And the product is just going to be 4 tau. Now I've set it up into an integral that I can handle quite simply. This is going to be a 2 tau squared, and it's going to be evaluated on the limits t minus 1 to 1. If I go ahead and do that, I'm going to get a 2 minus, right? And I'm going to have a 2 times t minus 1 quantity squared. If I go ahead and clean that up just a little bit, I'd like to try to get it in clean as possible. I'm going to get 2 minus, and I'm going to have 2 times, and if I expand out that t minus 1 squared, right, I should get a t squared minus 2t plus 1, something like that. Now what you'll see in there is that I get a 2 minus 2, so the 2's cancel, and I'm going to have a minus 2 t squared, so a minus 2t squared, and then I'm going to have minus 2 times minus 2t, that's going to be plus 4t. So I should have a minus 2t squared plus 4t. And that's probably as simplified as I'm going to get it. The next region picks up where the last one ended, so it's going to pick up at 2, right? And this is where the h pulse has completely exited the triangle function. So we know that that's going to go out just because of the nature of these two waveforms out to infinity. So this is going to be the last region. And in that particular case, we can again just show a representative case of that. Here's where the pulses has exited out, right? We can see that there is no overlap where both of those functions are non-zero. So I'm going to be integrating a 0 and just getting out 0. So this last region and the first region, both really easy to compute. The other ones took just a little bit more effort. Again, we'd like to put this final result and get it all into a single expression so we can take a look and plot it. We remember that the first region went from minus infinity to 0. The next region picked up at 0 and went to 1. The next region picked up at that 1 and went through 2. And the final region went from 2 out to infinity. So the first one was region 1, region 2, region 3, and region 4. The first region, where the pulse had not yet entered anything, we got a product of 0, integration of 0, that was just 0. Same thing for when the pulse had ended or exited, so that was also 0. And then we just have to go back up and grab our values. R2, the the region 2 had a value 2t squared, so I'm going to go ahead and plug that in there. I have 2t squared. The next one was what? It was a minus 2t squared plus 4t. I could put minus 2t squared plus 4t, something along those lines. Now, we can probably make a reasonable guess as to what this thing looks like, so I'll go ahead and plot it out. But as your expressions get a little bit more complicated, I really do encourage you to go ahead and use a package like MATLAB to make a nice, neat plot of these guys. So I'm going to be looking at what? X convolved with h as a function of time. I know that things are happening at 0, 1, and 2. Those are something to do with the regions, okay? So I'm going to go ahead and just try to do a little bit of different colors in here. I know region 1, right, it was all 0, so there's my region 1. If I move into region 2, it was 2t squared. That is a convex up quadratic function. If I put in the leftmost limit 0, I'm going to get 2 times 0, so I should have a value of 0. That's nice. That's functionally continuous with my other region, region 1. That's a good sign. Remember, we were looking for jump discontinuities as being indicators of maybe doing a math mistake. So I'm pretty happy so far. It looks like things are lining up. And then I'm going to go to the other side. If I take 1, so I'm going to have 2 times 1 squared, that's going to be 2. So come up 1, 2 units, right? And I know my other point out there is that. It's a quadratic function, and it's a quadratic pointing up. So we're going to get something like that. That is my region 2. We know that region 3 is also a form of quadratic. This one is going to be this is going to be convex down, so it's going to be pointing, the kind of curvy part is going to be pointing down. And I'm again going to just try to figure out what it is at the two edges. Let's go ahead and put t equaling 1 into this expression. If I put t equaling 1, that edge into minus 2t squared plus 4t, 1 squared is 1 times minus 2 is minus 2 plus 4 times 1. That's going to be plus 4. So minus 2 plus 4 is 2. So I should be getting a value of 2, right, when t equals 1. I'm very happy again to see that because that lines up exactly with where my last region ended, right? My last region ended at 2. So again, I'm going to get functional continuity here. That's a good sign that things are going well. If I'd had a jump discontinuity in the convolution of 2 functions that did not have delta functions, I wouldn't expect to see any jump discontinuity. So I'm just using this as a diagnostic. If I go to the other end, so when I'm looking at t equaling 2, I'm trying to figure out what this guy equals. I hope it equals 0 because I know that's where my final region ends up. So let's see what happens on there. Put 2 squared, that's 4, times minus 2 is minus 8. And then I'm going to have minus 8 plus 4 times 2. So minus 8 plus 8, that is 0. So this guy does indeed evaluate to 0 at the other edge. It was a quadratic pointing down, and so it's going to look something like this. If you wanted to have it really, really accurate, you do something like MATLAB. So this is my region 3 in there. And then I'm just going to go ahead and pick another color. It's going to look a little weird, but I'll put it in yellow. So I know region 4, right, which is 0 everywhere. I got a result that was functionally continuous coming out. It's a piecewise constructed function. My original function, x, was a ramp function, right, that had 1 in width. My other function was a pulse, also of width 1, and we convolved them together, and we saw we get this kind of skewed looking pulse that is 2 units in width. It goes from 0 to 2, something along those lines. In every case, when you go through this convolution procedure, you should do separate work for each of the different regions, and you should pull everything together into a single expression and plot out the result. Take a look at that result and make sure it's making some sense. Okay, so let's transition a little bit here. Let's talk the convolution properties, or some properties of convolution. These convolution properties really are just some mathematics that help us better understand the convolution operation. They gave us insight into the convolution operation as well as its application to things like signals and systems. And it gives us some options in proceeding with the mathematics of trying to evaluate things like convolutions where we have some choices and maybe we can pick the easier choice so it can simplify our lives. Getting good with these properties gives us additional insight, right? And also can make things easier. The first property, and I've gone ahead and written most of these out. Most of them are going to seem kind of familiar because you're going to see properties that look somewhat like maybe properties you saw for multiplication. And so some of these won't look terribly surprising or unusual, but we definitely want to establish that they are indeed available so that we can use them with confidence. The first property is the commutative property. If you look at the root word there, commute just means movement. And so a commutative property basically says the order of arguments for a convolution operation doesn't matter. X convolved with H is going to give you the same result as H convolved with X. It doesn't matter whether I convolve X with H or H with X. I can interchange the order of those guys. It shouldn't make a difference to the result. How might we use this? Well, we know that convolution is an operation through our three-step procedure, right? Involves taking one of the signals and then taking the other signal and flipping and shifting it. Well, sometimes that flip and shift operation, especially if the underlying signal is kind of complicated, that flipping and shifting just makes it more complicated. This commutative property, this commutation of convolution property, tells us that we don't have to flip and shift just H. We could flip and shift X, right, and leave H alone. So you flip and shift whichever one you like. You flip and shift whichever one is easiest, and you should get the same result. Most of these properties are just boring to prove, so I'm not going to spend a huge amount of time with proving, but I will show in this case, and if during recitation you want to see any other proof, just let me know and I'll be happy to prove it. But let's go ahead and prove this one just to show that the proofs don't have to be too bad. As a proof here, I'm going to just start out with the left side of what we said the commutative property is. X convolved with H. We know by definition that's an integral of x of tau, h of t minus tau d tau. I'm going to do a variable substitution. I'm going to let tau equal t minus tau. That gives me tau equaling t minus tau prime, right? And d tau equals d tau prime. If I go ahead and make those substitutions in there, x of tau becomes x of t minus tau prime. H of t minus tau becomes h of tau prime. D tau becomes d tau prime. I do have to worry about my limits of integration. If I had tau, right, or my tau being minus infinity, right, then I should be getting this, and I got a small mistake in here. D tau is not equal to d tau prime, it's equal to minus d tau prime, so there would be a minus d tau prime. So you could think of there being a minus sign in there. But my limits of integration, right? My limits of integration are gonna get swapped as well, because as my lower limit when tau is equal to minus infinity, right? When I put tau equaling to minus infinity, I'm going to get a minus minus. Let me put this into a different color. So when my original limit of lower integration was minus infinity, and I'm looking at what happens to tau prime, right? I put a minus infinity in here for tau, and I negate it. That's going to be plus infinity plus something is just going to be infinity. So that minus infinity, right, is going to go to an infinity term. If I look at the infinity up on the upper limit, I put infinity into that tau. I'm going to have a minus sign in front of it. That's minus infinity. So that infinity term is going to go to a minus infinity term. When I have limits of integration that go from a positive number to a negative number, I know that I can swap those guys by negating the integral. And that's where that absorption of that minus on the d tau is going to come into play. So in the end, what do I get? I get an integral minus infinity to infinity. I skipped a step in here basically. So I get an integral from minus infinity to infinity of h of tau, x of t minus tau d tau, basically with primes on there. It doesn't matter what we call it. We're integrating that variable away. Shouldn't make a bit of difference. So we end up with what we recognize, right? It's just being h convolved with x. So interchanging the order doesn't make a bit of difference. We can get it through a change of variables. As I mentioned before, this commutative property does give us some options, right? We can just pick whatever is the easiest order to do the convolution. If it's easier to flip and shift x, do that. If it's easier to flip and shift h, do that. You'll get the same result. Distributive rule. The distributive rule looks something like the following. If x is convolved with the sum h1 plus h2, we can distribute that convolution operation so that the result is x convolved with h1 plus then x convolved with h2. So we can distribute convolution much like you've seen distribution of multiplication back when you were learning algebra. Graphically, there's a really beautiful interpretation to this property. This property, I'm going to start out by looking at what is on the right-hand side here. X convolved with h1 plus x convolved with h2. Think of this from a systems standpoint. X convolved with h1 is like a signal x, right, going through a system h1 to generate an output. If I look at the second part, x convolved with h2, that's like that input x going through a system h2 and giving me an output. And then what am I doing? I'm just adding those guys together. So take the first output and the second output, get a total output. So if I was going to look at that right-hand side of the equation and make a block diagram, this looks like a single input x feeding into two systems that are in parallel, and their outputs are just being summed, okay? If I look off here at the left-hand side as to what that's equal to, that's x convolved with the quantity h1 plus h2. X convolved with anything, as a systems perspective, is x feeding into a block whose impulse response is that anything. Here, the anything is h1 plus h2. So x going through a system with a combined unit impulse response of h1 plus h2, right, is the same as that system in parallel, where you've got a system h1 in parallel with system h2. This distributive rule, really, as far as a systems perspective, tells us how to deal with systems in parallel. If you have a system H1 in parallel with a system H2, you can come up with an equivalent single block system, right, whose impulse response is just the addition of the two individual impulse responses, H1 plus H2. Really easy to find the overall impulse response of the combined, the total functionality of those systems in parallel. You just add their impulse responses. So systems in parallel, right? The overall impulse response is just the sum of the individual impulse responses. Again, you can prove this much like we did on the other one. You just plug it into the equation. It's a little tedious, really nothing too much to be learned. I encourage you to do that on yourself on your own time if you find it worth looking at. Associative property, the associative property looks something like this. X convolved with the quantity H1 convolved with H2. And that's going to be equal to X convolved with H1 as a quantity, then convolved with H2. Associative is groupings, right? And it basically says it doesn't really matter how we group arguments of convolution, right? That I can convolve H1 and H2 and then convolve X. Or I could have convolved X and H1 and then convolved H2. And if you mix this with some of the others, we know that we could interchange the orders. So there's all sorts of stuff that we could do as far as reordering and grouping, and it shouldn't make a bit of difference on the output. Again, we can come up with a picture, a systems picture on this that can be very helpful. Let's again start off on the left-hand side, and let's look at that interior guy inside the parentheses. X convolved with H1. What is the systems level perspective of this? That's an input X going through a system H1, giving us an output. The output there is just X convolved with H1. If that now serves as the input to another system H2, the overall output of that system, right, is just going to be whatever that input was, in this case, X convolved with H1, convolved with the second system's impulse response, H2. So this right-hand side here, right, this X convolved with H1 as a quantity, then convolved with H2, could be graphically viewed as X going through a system H1 in series with another system H2 to give us some output. If the associative property is true, this is the same as X convolved with just a single thing, right? So that's like X going through a single system, a single system block. And that single system is going to have an impulse response that can be gotten as just the convolution of the two individual system impulse responses, H1 and H2. What this tells us, what this associative property tells us, is it tells us how to deal with systems in series, right? A cascade of systems. If I have a system H1 in cascade with another system H2, it is assuming that these systems aren't loading one another. But if I have a system H1 in cascade with a system H2, I can come up with a single system representation, a single system equivalent, right? That has an impulse response that's just the convolution of the individual impulse responses. So systems in series, right? To get the equivalent impulse response, you just convolve all their individual impulse responses. So two different properties. We have that distributive and associative telling us how to handle systems in parallel and also systems in series. There's a shift property as well. The shift property says something like this. If I have a signal X convolved with another signal H to give me a signal Y, then if I shift either X or I shift H, then I get a corresponding shift in the output. So shift one or the other, and you get a corresponding shift in the output. This makes sense from a standpoint of a system, right? If you look at this upper one, the if, this is like an input X going through a system who has impulse response H gives us some output. This sum down here says, hey, shift that input, right? Run it through the same system, and what do you get? You get a shifted output. That's not a surprise. You delay an input going into a system, you'd expect the output to get delayed. Because of the interchangeable order of input and the impulse response, we could get the same effect by shifting the impulse response function as well. A shift in either X or H causes a corresponding shift in Y. Again, something that can be visualized quite nicely just by thinking of it in terms of system block diagrams. I would put a warning on this. If x convolved with h gives us y, notice that x t minus cap t convolved with h t minus cap t does not equal y of t minus cap t. In other words, you can't shift both of those things and only get a single shift in the output. This might be a little bit surprising because I think in mathematics we get really used to taking things like some equation and then doing something like this. We substitute t for something like t minus cap t. That would lead to this expression, and I'm telling you, hey, that's not true, and it's definitely not true. So you can't just willy-nilly substitute for the independent into the argument of our functions when we're doing a convolution. You have to be really, really careful. And the reason for this, or the kind of the answer to this mystery, is that this is a shorthand notation. This is a shorthand notation. What is the shorthand notation? Xt convolved with ht is really integral minus infinity to infinity of x of tau h of t minus tau d tau, right? Now, if I want to substitute t going to t minus cap t, right? And I look at what that convolution actually is, there's only a single t to do it. There's not two t's. So this notation over here, the shorthand notation, is lying just a little bit because it makes it look like there's two t's when really there's only one. So we've just got to be careful. I would say that you have to proceed carefully with shorthand notations, and if in doubt, you just go to the underlying true mathematical definition, and that would probably steer you in the right way. This brings up just a little kind of difference. So here in the USA, we tend to represent convolution in US programs of electrical engineering and others. We represent convolution using the following notation. We say x of t convolved with h of t, so x of t asterisk h of t, and we define that using our convolution integral, just like it needs to be. The convolution integral is the thing that is constant. Most of the rest of the world, they have that same convolution integral. I mean, the rules of systems haven't changed, but they use a slightly different notation. They use x star h, and then they just show t once. They show that as a function of a single variable t. I will tell you that in some respects, I like this notation better than the US notation because it's less likely to have you do something like this, where you make a variable substitution, which we've known and done and used in algebra, and it doesn't let us get into trouble like we would with this US notation that's a little bit wonky. However, with that said, I will say that the US notation allows you to do a separate shift of x and a separate shift for h and deal with two different shifts of those two functions, and it kind of lets you do that easily. That's not so easy here. You can't figure out how to shift x separate from h. So no matter what, these shorthand notations have limitations, right? They both have their own kind of deficiencies, and I don't think we necessarily have to get too hung up on it, but we do have to know what the deficiencies or the limitations of notations are and just be aware of where they can get us into trouble. Two more properties, and then we should be done with this. The identity property basically says what? That x convolved with something should be able to get us back out x. This is the convolution identity. And the thing we need to convolve with is a delta function. The proof here is real simple. Let's just write this in terms of the convolution integral. This is an integral minus infinity to infinity. I'm going to put in x of tau, take the other function, which is delta, and I'm going to do a flip shifted version. T minus tau d tau. Well, guess what? This is just the sifting property. We've already seen that before. Using the two properties of the delta function, we know that this gives us x of t. We are done, right? So this x convolved with delta giving us back x is just a statement of the sifting property. Last property we have, the width property. If x of t has a width, call it tx, and h of t has a width th, then the convolution of these two has a width that is just the sum of their widths. We can easily prove this. I'm going to prove it graphically. I'm going to go ahead and think of x as being a function that has some width t, so it's going to start at some value a and end at a value a plus tx. Same thing for h. It starts at a value b and ends at a value b plus th. So x is of width tx and h is of width th. If I flip and shift h, which I know I need for the convolution, right, it's going to still be of width th, but it's going to go from minus b minus th to t minus b. The convolution between these two has what? The output y is going to start where h, right, starts overlapping or hitting x. When does h start hitting x? It hits x when this edge of h hits that edge of x, or when t minus b equals a. Solve that out and you get t equaling a plus b. So the result y has its first non-zero value at t equaling a plus b. In the same sort of way, right, we know that y is going to end when the trailing edge of h finally exits and completes going through x. That's when t minus b minus th is equal to a plus tx. If you go ahead and solve that, you get t, right, equaling a plus b plus tx plus th. So if I want the overall width, right, the width of t of y, ty, so the width of y is ty, it's just the end minus the start, and if you do those two calculations together, you get tx plus th, which was the width property. That ends us out for this convolution discussion. Next time we'll do some final notes in chapter 2. We'll talk a little bit about system stability, both internal and external, and we'll do some intuitive insights into low pass filter behavior, and then we'll be done with chapter 2.